What do you see this page? PBR.
Do you know where is the washroom? The washroom.
The bathroom?
Yeah, the restaurant. Yeah. No. Okay. Thank you.
What's this one do? If anything, it reduces this knob? Yeah. What's this do? That's for like... Oh, I see. Yeah, it's not. Yeah, I don't think it does. There is a pole in there. It is? What's that one do? Ooh. Oh, nice. Are we good? I think we're ready. Is he gonna introduce? Yeah, he's going to introduce.
Or you're in security, you like to be secure.
Whatever you're making will be Don't ever trust it. First rule.
I'd like to welcome all of you to Skydeck. As you can see, we have a beautiful view here, and it's described as the last step in the Berkeley ecosystem when they accelerate companies who already have customers to get fundraising and move up into seed and Series A and then IPO now. And we have a lot of great companies which are in the back there, and we use this as our event space. We have more than 12 companies doing a lot of great things, including some companies that have 150K in revenue, and they bootstrapped from nothing and haven't yet taken funding. So a lot of great companies at Berkeley and at Skydeck. So I'm Mark Godwin, the founder and CEO of Automa Systems, and we're bringing machine learning technology to trucking. And I'm going to give you a little talk about our company, and then I'll turn it over to your speaker. So we're bringing real-time logistics to transportation, and our broad vision is fully automating trucking. And so when we say fully automating trucking, we actually mean fully automating trucking. So my experience with drones and self-driving cars, including the Berkeley City driving team, and a startup which built Google Street View, and then got acquired by Google. And so the first step in this process is automating dispatch operations. And then once you control that connection between supply and demand, you can use machine learning to maximize SRI, and then finally, about 5 to 10 years down the road, we can open the market to self-driving trucks. So what is the problem for trucking companies and throughout much of transportation? And it's threefold: underutilized vehicle assets, human dispatchers, not because they're bad at their job, but because they can't look through 10,000 assets or trucks simultaneously to make the right decision. And then finally, ad hoc and outsourcing. So that means they have just enough trucks to satisfy their base demand, and anytime they go over that demand, they have to outsource with other companies. And they currently do that with cell phones and radios, and we can help make that process better. And then finally, the solution is optimized real-time vehicle routing and dispatch, and in particular, using technology to minimize the running costs and maximize utilization, and then creating a marketplace for trucking with automatic in and out sourcing. So I don't want to bore you with slides, or I want to get to your speaker, but I can give you a quick live demo of our product. And I think it will make a lot of what I'm saying much more clear. So what you see here is a bunch of vehicles that are real and moving through the Bay Area, and we're tracking their current position, and in particular the profit margin of the fleet. And then we're not only tracking what it is now, but we're predicting this profit margin through time. And then you can see that we're actually tracking the current state and the future state of each of these assets, and then predicting, for example, they're going to drop in 60 minutes, or they're waiting for a customer to load. And so we're tracking a lot of information. We know the pickup and drop-off endpoints. And then the more exciting is the map. And so what you see here is where the vehicles are and where they're going. And you'll see them update and move along throughout the Bay Area. But then the really exciting part, and what makes this problem so difficult, is that we're tracking where the vehicles are and then planning to the future up to 24 hours. And so as I switched from one-step horizon, or just looking at the next step, to horizon mode, and then stepping through time, we can start to display, assuming the internet works, so what's happening out into the future throughout the Bay Area. And then switching back to realistic paths, you can see the actual paths that each vehicle is going to take and that we're predicting. And so the exciting about this technology is that we're tracking the fleet, predicting the future, and we can make decisions which help minimize or maximize their profit. So for example, if there's a traffic jam on the 80 that impacts the profit margin of the fleet, then we can help them through recommendations and through automatically making decisions for them, help them adapt to that impacted profit margin. Anyway, so I hope that was interesting. I'll be here the whole night, and if you want to talk more, always excited to talk about it. And the only thing that makes this technology possible is massively parallel machine learning, or massively parallel infrastructure, where you can make sure to keep the algorithms at same speed, even though vehicles might grow up to 100,000. All right, thank you, and we have our great speaker coming.
Hi, I'm Shivaram, and today I'm going to be talking about this project that I've been working on called SparkR, which is an effort to let you do interactive analysis from R at scale. This is joint work with Xiong Han, who's an undergraduate student at UC Berkeley, and we're both part of the AMP lab at UC Berkeley. So before I get started, let me get a show of hands. How many people in this room have used Spark in one form or the other? Like writing demos, okay. Cam stuff like that. How many people in this room have played around with R? Like they didn't at least one R. Oh, that's awesome. Okay. So I have a crowd. I was wondering if I should stress more on how Spark works or how R works. I have a crowd that's knowledgeable in both of them. So this is going to be awesome. So when you think about Spark, what are some of the keywords that come up in your mind? What comes up in my mind is things like it's fast, lightning speed query distributed computing. And the second thing that you think of is that it's scalable. So you can throw a lot of data at it and it scales very easily. And the third thing that you might come up with is something like you have this nice interactive shell where you can tie up your computations and you can even run things on a really large cluster from an interactive client. You can try a similar exercise with R, and when I tried it, the three things that I came up with was, they're like stats, you know. So R is like a project to do statistical computing and has some great features to do statistics stuff. Right? But it's not just the base features. R has an extensive list of packages that are invaluable, that compute everything that you can think of. And so if you want to think of a way to do something in R, if you search for a package, you'll probably find it. Right? And the third thing that I came up with was it has a very nice interface for plotting things and visualizing things. And this is not just the base API, but also things like ggplot2 and all of these great packages that just make it such a nice place to work with for visualizing things. So the aim of this project is to put both of these things together. Wouldn't it be nice if we had a system that could be fast, scalable, interactive, and let you do stats and plots and use all these extension packages? So this is the goal of SparkR, and today I'm going to tell you how far we've gotten towards this goal. We have an alpha release, so in the first part of the talk, I'm going to talk about the features that we support and how you can go about using it. And the second part, I'll open the wraps a little bit and show how this works and what are some of the tricks of the trade. To start this talk, let's take a high-level view of what does Spark enable for us. And what Spark enables is that it provides this nice API in this high-level module called the RDD. Right? Many of you, since you've used Spark in this room, will be familiar that there are an extensive list of transformations and actions you can do on an RDD. And the nice thing about them are they're composable. So you can apply a map and then do a filter and thus build up your entire computation using these RDD operations. So when we first looked at this, we thought, how do you make it suitable for RDDs to be used from R? Right? One way is to directly map them, but you also want to make them so that it feels natural, like when you're writing R code, to be able to use RDDs as a part of the R code. But it turns out the mapping is actually very simple, and that's because of this facet of R, which is very useful. And this is a quote from one of the mailing lists where it's actually an article about how to use apply in R. And the code, it goes like, how do I use loops to do anything in R? And the answer is don't use loops. You should use one of these apply template functions, which lets you work on a collection of objects from within R. Right? And when you stare at it from a little bit of distance, what this apply function looks like is exactly what a map function in Spark is looking like. Right? So it's actually very natural to put together these two concepts and to extend the notion of RDDs to be used from R, except using the apply interface now instead of calling it a map. Right? So that's what we set out to do. So we put R and RDD together, and we could have gotten an R2D2, except we didn't get an R2D2, so we got something else, which is called an RRDD. Okay? And these are the list of functions that the RRDD supports. This list looks really similar to the previous list that I showed you, like 2 slides back, except for the ones that I've highlighted in red out there. These include things like lapply on an RDD now, and lapply partition, where you can work on a partition of the RDD in parallel. And I'll also talk a little bit more about include package, which is this new directive that we added up. So the best way to look at an API is to look at code, look at examples, and since it's the 101 or the hello world of distributed computing is like word count. Let's start from word count, okay? And this is exactly plug and play. This is exactly taken from the examples that we distribute with SparkR. So this code can be found there. And the first line is you're reading an input file using a Spark context. This line, there's not much to explain there, except for the fact that we pass the Spark context around as a member, as a function argument, instead of calling a function on the object. Then the next two steps are you have a line, and you want to pluck out all of the words from each line and count the number of and count the occurrences of each word. So we use a flat map and an lapply. As you can see, the way the syntax works is you pass a function. You can inline pass a function to something like lapply, again similar to R, except for the fact that words here is an RDD, not a list in R. Okay, and once you've done that, you can then perform a reduction. Again, natural Spark syntax by calling reduce by key. Note that you can pass existing R functions like the addition function, just like you pass it to a function like the reduce operator in R by calling the plus in quotes. And the final step is just fetching all of the counts to your driver machine. So this gives a very high-level, nice overview of some of the basic operators that you can use in SparkR. And now we're going to go one step further and look at how you can do all of this with a live demo. Okay? And what we're going to do in this demo is we're going to take up a reasonably complex machine learning task, which has some real input data set, and we're going to walk through how you do this in SparkR and see what are some of the pros and cons. What are some of the powerful things you get by combining Spark and R. For this, we're going to start off with this data set, which is this endless data set of handwritten digits. So the data set is a bunch of images which all have numbers that have been taken from a large number of users. And the machine learning task here is to identify what number or what digit is there in each image. This data set has been used for a while in the vision community or like in the object recognition and community. And there are a lot of algorithms to solve this with high accuracy. So we're going to do one such algorithm today. And the steps of the algorithm are, we're going to take the raw input data set, and we're going to pre-process the data set. And Spark is really good at doing this in terms of, it's like an ETL like process, but it's a featureization process here, right? And what we're going to get out of this is we're going to get two matrices out of this. One which I'm calling A, which is the feature matrix, and the other one which I'm calling B, which is the training data or the label matrix for the training data, right? And then we're going to throw some machine learning at it to figure out the best model that we can learn for this existing data set, right? And we're going to then see how well our model fits and like what's going on. So let's see how this is going to work. Awesome. So I have a Firefox window open here. So I'm doing this demo using this tool called RStudio. I guess if you used R, you're sort of familiar with this, but it's this really nice IDE which has a web UI. So this demo is running on EC2, but I can show it just using a web browser. And there are three gains in this, and we'll start off looking at this code pane at the top left corner. And I'm just going to kick off the existing code that I have so that this runs in the background while we walk through this code. So I just hit run there. And the first line, which is sort of important in all of these SparkR programs, is to include the package. Okay, that's pretty obvious. And the other thing that I do is I include other packages that I'm using as a part of this exercise.
Can you make it bigger?
Sorry?
It's possible to make it bigger?
Yes, I can make this bigger. So options. Oops. Shouldn't have made it bigger. That's fine. I think it's just reloading the session. Okay, it's back. So there can be only one browser session open at a time.
Control plus.
Just control plus. Awesome. This is better?
Yeah.
Yeah. Cool. nice thing is that we reconnected to the same session, so it was running in the background all the time. Okay, so let's just walk through this program line by line and see what goes on. So line number 9 here initializes the Spark context. This is like creating new Spark context in Scala, except there's a helper function called SparkR.init. And I'm just using a single machine here with 8 cores, so it just says local 8 here. And the next line, I just read the input data in, which is text file of SC. The next few lines initialize a bunch of constants which are used in this algorithm. There's nothing much interesting going on there until line 23, where I have these matrices which are used to generate random features, and these matrices are used in every task. So it's better if we can broadcast them instead of shipping them with every task. So I create a couple of broadcast variables, which is again similar to how the Scala feature works. Line number 26 is the new directive that I was talking about before, where we can use third-party R packages as a part of your closures. So in this example, I want to use the matrix package to multiply some matrices and do some things with them. So I can write this command, include package sc, matrix, and before your closures are run, these packages are included in the environment, in the R environment that they are run. Okay? Note that we assume the packages are installed on the machines. This doesn't fetch and install the packages. It just includes them. It's sort of like shipping a jar around. So that part seems pretty simple. And the next 3 functions are executing the machine learning algorithm. The thing to note here is that I have functions like read matrix, which are in another file. I just sourced the file on top. It's in a file called mnistutils. SparkR automatically serializes the function, the closure, and also other things that it depends on. So this makes it very easy for you to structure your code, and you don't need to exactly worry about what is getting passed around to the different parts of your code. And having read in the file, I can run this random features, and I access broadcast variables using a value of the broadcast variable inside my inside the closure that you have. So what this random features does is it creates the feature matrix and the label matrix that we saw on the slides before we came here. So having gotten that, then we apply our learning algorithm, which is computing this A transpose A and A transpose B, like these 2 matrices, and that uses the matrix library to do this multiplication out here inside the closure, like line 45. And having gotten that, we can then locally solve for the model. So what I'm going to do is I'm going to run the second half of this code now. And the code's running below here, and if we can resize this thing, we can see all of the Spark log info messages as well. So you get all of the same information you get when you're using Spark. And having created the model, let's see how good our model is. So there's some test data, which is, so we have 60,000 images in our training data, and we have 10,000 images in our test data. And we can see how good our error percentage is by doing a prediction to the model that we just trained. So the prediction takes like a couple of seconds to run. Whoa, that is not what I was expecting. I'm just going to run this whole thing again so that I don't know what stage we got now. I think when we restarted it, it regenerated parts of the. Okay, so I'm going to let this thing run again and walk you through what the second half of this thing looks like. And the second half essentially is an effort to show what are some of the advantages of doing this in R versus, let's say, doing this in Scala or like Python or something like that. And the advantages in things like, once you've done your machine learning, you want to either visualize your model or you want to figure out where the model went right and wrong. And there are a lot of tools available or packages available in R which help you do things like that. So, for example, there's a package caret that I'm using here to generate this confusion matrix. The confusion matrix is this nice term which is intuitively sounds, and it actually does exactly what you think it does, which is that it figures out how many mistakes you made or how many times you got confused for each of the digits. So in this example, how many times did we guess 1 when we should have guessed 7 or something like that, right? And there's nice tools to visualize these confusion matrices as heat maps that we're going to do here. But it's not just that. You can also get exactly which image went right and which image went wrong, and you can try to do more debugging and things of that sort using more powerful tools that you have at hand inside R. So let's see how far our computing matrix has gone. So this is running 2 sets of tasks, and the first set of tasks just finished, so it's running the second line. Yep. And this takes around 15 seconds or so. So after that, we can have a model that we can visualize. So, so we'll look at the heat map here, and we look at some of the images that went right and wrong. But the big idea here is that any other packages that you want to use and you want to integrate into your programs should be easy to do as well. Okay, great. So we got our model back now. Let's see how well this model does. So the error was like 5%, which is what I expected the error to be, not 100% as it was last time. All right, so we create the plot and then move this out. And this is the confusion matrix. So diagonal elements are where we want to be. So we want to say a 0 is a 0, a 1 is a 1. So having dark colors on diagonal elements is very good. Having dark colors on non-diagonal elements is not that good. So for example, if you see the box between at the intersection of 7 and 9, where we said that it was 9, but it was 7, but it was actually 9, we have a bunch of mistakes that we made of that kind, right? So this shows that there are some images that are 7 that are getting classified as 9. And I'm not much of a machine learning expert, but maybe we can figure out what you need to tweak in your algorithm based on that. We can also see what images did we get wrong. So this is one example we got wrong. We expected this to be a 2, but we predicted this as an 8. And we can play around with this a little bit more. And again, this was presumably a 2 written by a user, but this we predicted this to be a 6. So, that's how this works.
It's obvious.
Looks obvious, right? But actually, this one is even more tougher. So this one expected was 4, and we predicted as a 9. I actually think it looks more like a 9 than 4. But anyway, so you can keep playing around with things like this. The source code for this example and the data set is also available online. So if you go back and you want to try out SparkR, you have a few example applications to play around with. Okay, so let's switch back to the talk. So that demo, the parts of it that went well, are an example of how to use SparkR. Okay? So let's switch gears a little bit now and look more deeper inside into how SparkR works and what are some of the what were some of the key features that we built and how we built them. And to do this, we'll first start with a high-level data flow. Right? How is it that we're able to take these R computations and run them in a distributed fashion? Right? And the way we do this is we look at 3 different machines that we're using. So one is your driver machine, where you're writing your code, and the other are like 2 worker machines in your cluster. And the first thing you do is you say, let's say you launch R. So that launches a process on your local machine that is your normal R process, like vanilla R. And when you include the SparkR library, when you say library SparkR in your code, that includes all of these Spark context objects. That there's an R version of the Spark context object, like it includes that. And it also uses JNI bindings to start a Java Spark context on your local driver machine. Right? So you can go ahead, you can continue creating RDDs and making transformations and all that. And then when you hit an action, it then talks to these Spark executors, which are running on your cluster. So the Java Spark context, we use that to talk to the executors. And each of the executors then forks R on the worker machine and passes in the exact function that you want to run and the data that the function should be run on in each individual machine. And then it comes back the other way around and sends results back into the Java Spark context and back into your local R console. So this is sort of the high-level data flow of how this thing works. The most interesting part of this data flow is what goes on in these orange pipes, or what connects the Java Spark context and the Spark executor. So we're going to take a more closer look at what's inside these orange pipes and how do we get these objects. And there are 2 interesting things that I think SparkR does that I haven't seen existing integrations of R with other systems do. So the first thing is this automatic closure capture, right? And the automatic closure capture, we do that by walking up these frames of environments. So in R, all the objects belong to a particular environment. So when you're working you probably have your base environment that you start working with, and then there's a parent environment for that, and so on and so forth. And so from the moment where the action is triggered, we walk up all of the environments in the stack, and we figure out which are the objects which are being used. So we perform this resolution of this is what you refer to when you say weights inside your function. Right? And using this sort of walking up the stack, we're able to capture get all the objects that need to be shipped to the cluster, to the other machines in the cluster. And to actually ship to the other machines in the cluster, we just reuse R's serialization formats. So this is a very well tested, and actually it's a very frequently used thing. When you save your environment, when you're quitting R, you can save your environment. And so there's a serialization format that controls how your environment is saved to disk. We reuse the same thing, except we send this over a network instead of saving it over disk. And then we reload this entire environment on the other side, like inside Worker, when they launch a task. Since this is a very well-tested and well-used implementation of serialization, it's pretty robust. So any kinds of objects that you're using, we're able to handle that pretty easily. The second internal detail that I'm going to talk about is how this executor to worker communication happens, and what are the costs of doing this, what are some of the challenges in doing that. And specifically, how do you handle multiple transformations on an RDD? So if you've used Spark in Scala, you're probably familiar that when all the RDD transformations are lazily evaluated. So when you say map and then you say filter, it doesn't actually run anything, but when you say count, it runs all of the transformations at once on the data set, through one pass of the data. Right? This is a little challenging to do in R. For example, let's say you say flat map first and lapply, like we did in word count. The naive thing would be to launch R first, send flat map as a function, get it back, and then again say, do apply for me, lapply, and then get it back. Right? But this is expensive because every time you go on one of these purple arrows that you see there, you have to serialize the data, make it into a byte buffer, send it, and deserialize it, and so on. Right? So we have this nice thing which detects the fact that you are merging a bunch of transformations. It's called a pipeline RDD. And what it does is it fuses all of these functions into one function. And so anytime you run the action, you call R once, and you send it a bunch of list of functions to run. And it does the right thing by calling them the right sequence and passing the right arguments around. So this improves performance whenever you have these long chains of transformations that you see. So we have an alpha developer release. It's on GitHub, and there's a nice one-line command to install this. If you have DevTools installed in your machine, that is. And I'd encourage you to try it out, just to play around with it, even on a local machine. The default one just runs it locally. And the other interesting thing was, it was not very hard to implement SparkR. And this, I think, is a testament to how extensible Spark is. We just had to write around 250 to 300 lines of Scala code. So there's just one Scala file called RRDD in our entire project. And the rest of the code was written in R. And the other nice thing is we have around 549 lines of test code for 1,500 lines of R code. So it's almost a 1:3 ratio, which is pretty nice. And we have a Travis CI build, which is green and great. So we encourage contributions like pull requests, features that you'd like to see, or even bugs you find, and we'd be happy to talk about any other things that you want to see in SparkR. There's more stuff in the GitHub repository. There's a nice wiki page on how you can set this up on EC2 and run it on a cluster. All the Spark examples, which are done in Scala and Python, I have ported to R, so you can get a feel of Python versus R or Scala versus R in terms of a code comparison. And there are also some instructions on how to get it running with Hadoop too, and using Maven and all that kind of nice stuff. So what's coming up? There are a couple of big features that we are sort of in the pipeline that we are working on. The first one is that what I introduced to you right now was a distributed list API, where you can do lapply on a list in a distributed fashion. And the next thing would be cool to have is a distributed data frame API, where you can create an R data frame, except it's split up over a bunch of machines. And I guess if you're following the Spark dev mailing list closely, there's this new feature called Catalyst, which lets you deal with SQL-like tables as RDDs, represented as RDDs, that is being introduced. So we're working on this sort of bridge that can look like a data frame in R, but is backed by these Catalyst-like tables in Scala. And the second interesting bridge is this bridge between the machine learning library and R. So right now, if you want to use some of some more complex machine learning algorithms, you would need to figure out how you're going to map the data and what parts are going to run on which machine and when you're going to aggregate data and so on and so forth. But once we have this wrapper, you can directly call something like k-means from R, and then it'll actually do the clustering and then come back to you and say, these are the cluster centers that I found, or something like that. Or you can launch linear regression from R and actually do the regression on the cluster and come back. There are a bunch of other performance improvements that we're working on, one of which being that instead of launching R processes each time, we have these daemons running around so that you save a lot of time within each function. Instead of launching the process, you can save process state, and all the broadcast variables can live inside the R object that is on the workers. Okay, so in summary, SparkR right now is an effort that takes an RDD, presents it as a distributed list, and uses a similar API to lapply to let you process stuff on the RDD. It serializes closures automatically and lets you reuse our third-party R packages as a part of your distributed computation. And the key benefit is that you can combine the scalability of Spark and the utility that you find in R by using this bridge package. This is our GitHub website. You can send me emails. You can also post any issues you have, any questions to the Spark user mailing list, and we're pretty active on it and get back to you pretty quickly. That's all I have today. Thank you.
So before we switch to GraphX, why don't we do questions for Shivaram about SparkR? Yep, that mic works.
So, yeah, so one question, how do you call R from the Spark executor? Are you use R server?
So the question was, how do you call R from the Spark executor? So we just use there's a Java or Scala library to launch processes. So we just launch R script as a process, and then we have a shell worker.r file which sets up the environment, which deserializes the data which is coming in and loads the functions and does all of that stuff. So it sets up a nice little shell environment for your user-defined functions to run it. So we can get away without using something like RServe because of that. Yeah.
Okay. So does it mean, for each line of the data you're going to process, you need to launch a new
No, so we process each block. Oh, sorry. The question was, for each line of data, are you going to launch a new R process and do this? So we process at the granularity of partitions. So if you have a partition has like 10,000 rows, so then we serialize all of them, we send them to the R process using a socket, and we run the function on all 10,000 and come back.
So if one machine has couple, executed running, you're gonna start a couple, R server in this case. So for example, for one machine, probably you have 10 executor running.
Right.
Then in this case, you're gonna start 10.
Yeah. So the question was, in one machine, you have 10 executors running. Are you going to start 10 R processes? That is exactly true. So we have a one-to-one mapping between an executor and an R process.
So why do you guys don't want to use R server in this case to code, actively code the R?
So the question is, why don't we use R server in this case? There's a simplicity in directly working with R instead of going through another layer. And this architecture is also very similar to the PySpark architecture. So there's a nice amount of code and like structural reuse that are there across these projects. So that's mostly the reason why we do this.
Do you have any benchmarks for sort of large in-memory type algorithms running R Spark versus
Oh, that's a good question. So we don't have anything which is public and very nicely run and tabulated with results yet. I've done some ad hoc benchmarks, like there's a k-means example in Spark, and I've run the PySpark version versus the SparkR version just to see a performance comparison of how similar or different they are. This was actually a little bit before the pipelining and the other daemonizing performance optimizations I was talking about. So SparkR was a little slower, like 15–20% slower or something like that. But again, this was on a single machine, and it wasn't really well done with a large amount of data and so on. So that's something that we are working on, and it would be good to have. And it would also be good to compare against some other stuff like the R plus Hadoop frameworks that are around. Yeah, sure.
One more question.
Yeah, I'm novice to both R and Spark. So I have a question that you who decide how to split the worker. Is it R or is that Spark, or is R Spark, or why have to write something
Okay.
to say how many workers there are?
Okay, that's a good question. So most of this work is done, we reuse Spark for doing most of the parts of distribution, scheduling, and how data is partitioned and all that. Spark determines all that. This works very well in the sense that we reuse all of its functionality, and if there are improvements or bug fixes or anything, we just get all of that free, right? So, and to more answer your question of what do you need to tell the interface, usually the data partitioning and like how many parts you have is determined by the input that you work with. Let's say you read in a huge file, or you read in some data set. Based on how your distributed file system works or something like that, the number of partitions is automatically set based on that. But you can also pass another argument saying, I have an idea that I want so many partitions. And the rest of it is in terms of these high-level transformations, like calling apply or calling filter or something like that. And that part happens automatically as well. Like it automatically figures out that you have 10 parts on your data, so I should run 10 tasks. And it automatically schedules them and so on. So
say if I want to run the linear regression, right? If you do in the background that I have to chop into 10 pieces and put into 10 workers.
Right. So the question is, if you're running linear regression, then what would you do? So there are two cases. So one is if your input data is on disk. Like I started with these images on disk right now, and the file system chopped it up into some number of pieces. So that automatically created some number of parts that I'm going to be working with.
I don't have to worry about that.
You don't have to worry about it, yes. And you can just describe the computation you want to do in each part for your regression.
So we're running close on time, so you can ask Shivaram a bunch more questions after we're finished with the second talk.
Same last time. Yep, that's great.
So this is Shivaram, and he's a grad student in the AMP lab. And Dan Crankshaw is going to talk about GraphX next. He's a first-year grad student in the AMP lab, and he's been working on GraphX as a project.
Can you hear me? Yeah, cool. Thank you. So yeah, I'm Dan Crankshaw. I'm a first-year PhD student in the AMP lab working with Mike Franklin, and I'm going to talk to you about GraphX, which is one of the latest additions to the growing, rich Spark ecosystem. And GraphX is a large-scale distributed graph analytics platform. So this is joint work with my collaborators Reynold, Joey, Anker, and Mike Franklin and Jan Stoika. So graphs are pretty central to a lot of different analytics tasks. For example, if I wanted to analyze the Wikipedia data set, I might first want to figure out what the most important articles are. So I might first get my articles out of this raw XML dump. Then I might extract the hyperlink graph, run PageRank on that graph, and once I have my PageRanks, I can figure out what the top 20 highest ranked pages are. Or maybe I'm interested in sort of broader trends about the Wikipedia data set, in which case I might want to do topic modeling, which is a machine learning algorithm, using LDA, which is a machine learning algorithm, on the term document graph, which maps words to the documents in which they appear. And once I have this, then I sort of get a sense of which words correspond to which topics and what are the most important topics in the general English-speaking Wikipedia. Or maybe I don't even care about the content of Wikipedia, I'm just interested in Wikipedia as a community. In this case, forget about the articles, I just want the edit histories, I want the user information. So I can extract that into maybe an editor graph and run a community detection algorithm, do some social network analysis. And once I have my community detection, now I have a sense of which users are parts of which communities. And a lot of times, I even want to combine the results of lots of different analyses. So maybe I want to find out which topics are discussed by which communities. But central to all of these analytics tasks is a graph. So let's take a look at PageRank. What is the PageRank algorithm? PageRank is a way, it's sort of the foundation of the modern web and Google, and it's a way to identify the most important vertices in a given graph. It's a way to rank the relative importance. So to compute a PageRank, for a given vertex I take the weighted sum of all of my neighbors' page ranks. So how do I actually get this started? Well, I just sort of randomly initialize them, and then I iterate until I reach some convergence criteria. And the nice thing about this algorithm is that it's just a weighted sum of my local neighborhood. So I can compute a lot of these different page ranks all in parallel. And this is actually an example of a pretty common pattern in graph analytics. This is a pattern that we refer to as the graph parallel pattern, or vertex-centric computing. And the way this pattern works is I have some model or algorithm state that's associated with every vertex or every edge. And to update this state for a given vertex, all I do is I do some computation over my local neighborhood. I don't need to access the entire state of the graph, just the local state. And this is really powerful because it means I can update all of these states in parallel. So as it turns out, there are a lot of different graph algorithms that fit into this model. I have algorithms from machine learning, from social network analysis, more traditional graph algorithms like PageRank or connected components. And based on this observation that so many algorithms that are really central to a lot of different analytics tasks fit into this pattern, there have been a series of graph parallel systems developed. So we have systems like Pragle, which came out of Google, GraphLab, which my collaborator Joey worked on for his thesis work at Carnegie Mellon. And these systems do two things really well. The first thing that they do is they provide a specialized API that makes programming in this pattern a lot easier. And the second thing that they do is they exploit the additional structure that they know about. We're no longer operating on some arbitrary data set. We're operating on a graph. And based on this additional structure, they can achieve much better execution, much more efficient execution than, say, a sort of generic data parallel system. And this has real-world impact. If we look at running PageRank on the LiveJournal graph, which is a graph of about 68 million edges, we see that Hadoop, which is sort of the traditional disk-based MapReduce system, takes over 1,000 seconds to run 10 iterations of PageRank. That's pretty slow. Spark gives us a big advantage right away, bringing it down to about 350 seconds. But if we then transition from a more data parallel, more flexible system to a specialized graph system, we can bring this down to 22 seconds, which is a huge win. So these graph parallel systems are great at the PageRank type tasks, the graph tasks. And graphs are certainly central to a lot of analytics tasks. But it's not the whole story. In this example, we sure had a lot of graphs. We had the term document graph, we had the hyperlink graph, we had the editor graph. But we also had a bunch of tables. We used tables to extract our graph structure from our raw data. We used tables to analyze the results of our graph algorithms. And we use tables to combine the results of these different algorithms. And traditionally, the way an analytics pipeline like this would be done is you use one system, a system like Spark or Hadoop, to do your table-oriented computing, a system that provides a lot more flexibility and doesn't require as much structure in your data, but is a lot slower on these specialized computationally intensive graph algorithms or graph computations. So when you need to do that graph computation, you switch to a graph system. But having separate systems is both inefficient in terms of data usage and data movement, and it's kind of a pain for the user. Suddenly the user isn't just dealing with one large, probably pretty complicated distributed system, but is dealing with two. And has to figure out how to learn, has to figure out how to program these different systems, how to deploy them, stay up to date on the mailing lists, and they have to write code to get data out of one system and into the other and back and forth. And having been doing this week to run benchmarks, I can tell you, not the way to go. But even more than that, it's inefficient. Where the graph view and the table view is really just different ways of looking at the same data. You're not changing what the actual data is. And yet, in order to change between these views, you're copying data, you're moving it across the network, you're writing it to disk, you're serializing it and deserializing it. And a lot of these graph systems keep a lot of indexing metadata and things like that to make these computation is efficient. So every time you take the data out of the system and put it back in, you have to rebuild these data structures. So GraphX is the solution to all your problems. Rather than having separate systems for each use case, we do it all in one system. We can do it all in Spark. And the solution has sort of two components. The first part is a new API that blurs this distinction between what's a table and what's a graph. And the second part is the system, the actual GraphX system itself, built on Spark, that implements this API and allows you to sort of easily and efficiently switch between these views without having to leave the system, without having to duplicate your data. So how does this work? So by blurring the distinction between tables and graphs, what we do is we say, well, a table and a graph are really just logical views of the same underlying physical data. They're domain-specific views, and they each have their own set of operators. We want to use graph operators when we're looking at the graph view. We want to use table operators when we're looking at the table view. We want each of those operators to operate efficiently. We don't need to change the underlying physical representation necessarily in order to achieve efficient execution. So when we talk about graphs in GraphX, we have our collection of edges and vertices, and we have a set of properties associated with every vertex. So the natural way to decompose this graph into a table is to store our vertex properties in a vertex property table along with the IDs. And we also have a set of edge properties. And so we store our edge properties in an edge property table with a source vertex ID and a destination vertex ID. So now that we've blurred this distinction between graphs and tables, we have a set of tables, and we're in Spark. The natural thing to do, and we call this the property graph. And once we have this property graph decomposed into tables, the natural thing to do is to use Spark RDD operators, which are already built in. We didn't have to do anything. And suddenly we have these efficient table operators on our data. We can do things like map, filter, join, and so on. So that's the table side of the story. But we also have efficient graph operators. They can operate on the property graph and the graph view of the data. So the first operator is this graph constructor, which is what allows you to switch from your table view. It tells the system, I'm switching from my table view to my graph view of the data. And to go back the other direction, we have sort of table constructors, which tells the system, all right, now I'm switching back from my graph view to my table view. But these are just logical switches. We're not changing the data at all. And then we have this triplets operator, which is a way to combine, it's basically a join between the vertex table and the edge table. And I'm going to talk about that a little bit more on the next slide. All right, so once I have my graph, I can get my graph from tables. I can go back to tables from graphs. What if I want to operate on the graph? So I can do graph transformations. I can both do structural transformations. I can reverse the direction of all of my edges in the graph. I can take a subgraph of my original graph based on an edge predicate or a vertex predicate. I can transform the properties of my vertices or my edges without leaving the graph view. I can bring in external data into my graph view without leaving that logical graph view by joining a table, an RDD, with my vertices or my edges. And I can compose all of these operators. And finally, I have this map-reduce triplets operator. This is sort of the holy grail of the GraphX system. And this is what allows me to do actual graph computation on my graph. So let's look at this triplets view and this map-reduce triplets operator. It's a little bit complicated. So for my triplets view of the data, I start with my edge, and I do two joins. I join with my vertex property table once to get my source vertex property, and I join with my vertex property table again to get the destination property. So this is a three-way join. And now that I have this sort of complete view of my data, I've unified the edge table and the vertex table. I have this MapReduce triplets operator, which basically does a group by aggregate over the local neighborhood of every triplet, or of every vertex. That's kind of confusing. So let's take this example graph, and let's look at what the MapReduce triplets operator means for just the vertex A. So let's ignore the rest of the graph. So the only triplets that this operator is going to operate on for the A vertex is my triplet BA and my triplet CA. So the first user supplies a map function, and that map function is applied to each triplet concurrently and emits some result. And then the second thing is the user supplies a reduce function, which takes the result of the map function and aggregates it, and now puts in a new result. And this becomes the new vertex property for A. So this is expressing that graph parallel computation of my local neighborhood. But this is sort of a complicated operator. But honestly, it would probably take me a little bit longer than a slide to really get the point across. But the good news is, you don't actually need to use it. Pragle and GraphLab already have these really nice, easy to use, vertex-centric APIs that make it really easy to express these graph parallel computations without wrestling with this MapReduce triplets operator. And as it turns out, these GraphX operators that I just explained are actually powerful enough to express both the Pragle API and the GraphLab API in less than 50 lines of Scala code each. But you can use the MapReduce triplets operator or any of the other graph operators. And the key thing is that you can compose them, and you can compose them with the table operators that Spark already provides to construct your entire graph analytics pipeline in the single system. You don't have to go from Spark to GraphLab to Spark to GraphLab and back and forth again. You can do it all in Spark. You can write all your code in the same files, and you only have to deploy one system. So now I'm going to walk through how we actually design this system and how we're able to efficiently express these graph operators in a sort of table-oriented system like Spark. I'm going to walk through how we distribute the data and some optimizations and some indexing and metadata that we store to make these operators efficient. So we have this property graph. This is at the heart of GraphX. But we know we're in Spark, so we know we're going to have to put it in RDDs somehow. That's how we store data in Spark. So the first thing is we store our vertex property table. It's just an RDD that stores exactly that table that I showed you before. It stores the vertex ID mapped to the vertex property. And that's just distributed using a hash partitioning scheme. Pretty straightforward. To distribute the edges, we use this 2D vertex cut heuristic. So the vertex cut means that every edge appears in exactly one partition, but that I might have a vertex, for example, A or D in this graphic, that has edges in multiple, that is part of edges in multiple partitions. And this 2D heuristic is, there are lots of different ways I could partition my edges across my cluster. And this 2D vertex cut heuristic is a way to get a nice upper bound on the amount of communication I'm going to do when I need to join my vertex and my edge table, which, if you'll recall, is sort of the heart of my triplets view and the heart of my graph computation. So the less communication we can do, the more efficient this operator will be. So we've got a nice upper bound on how we distribute the edges, but to reduce the communication costs even further, we store this index, this routing table, along with the vertex RDD, which tells me exactly which edge partitions I need to send a given vertex to when I'm doing this join. So, for example, I only need to send B or C to a single partition, and when I'm sending A to multiple partitions, I know exactly which ones I need to send it to. But communication is really our bottleneck, so we do play some more tricks to reduce the communication costs even further. One thing we do is a lot of these graph computations are pretty iterative. You're doing the same or similar types of operations in a while loop, basically. So you're doing a lot of these joins. So what we do is after we do a join, we cache the results of the vertex property join with the edge partition. And if all the vertex properties are changing, that's not all that helpful. But as it turns out, in a lot of these graph analytics pipelines, we have a case where most of the vertex properties have converged to some value. Say we're computing PageRank. Most of the PageRanks have converged, and we just have a few outliers that have a lot of neighbors or are part of some long chain that are taking longer to converge. So in that case, we only have a few vertex properties that are changing. And so what we can do is rather than shipping the whole vertex property, doing the whole join, we just do this incremental update that it just invalidates those parts of the cache that have changed. And that actually results in a pretty big win. We do a couple runtime optimizations as well. These are taken pretty directly from the database literature. So if you recall, this triplets view required a three-way join. I need to join the vertex property table with the edge table to get the source vertex property and the destination vertex property. But in a lot of algorithms, once again, PageRank for example, we don't actually need both the source and destination vertex property. In PageRank, R sub j, the destination vertex property, is never used. In this case, we don't need to do that join. So to detect whether or not we need to do the full three-way join or can eliminate parts of it, we inspect the bytecode of the user-defined map and reduce functions. And if we detect that a property is not used, we don't do the join. And for every join that we can eliminate, we reduce the communication cost for that MapReduce triplets operator by about a factor of 2. So that's a pretty good overview of the GraphX system and how it incorporates with Spark. So let's look at some performance numbers. So this is that same performance comparison, but this time we're going to throw GraphX into the mix. So we have our data parallel systems as the baseline. We see the Giraffe, which is another open source JVM-based graph analytics system, but still just a specialized graph system. It doesn't do this unification of graphs and tables. And that beats the baseline data parallel systems. GraphX beats Giraffe by another couple of factors. And then we get GraphLab, which is sort of the state of the art in terms of performance. And here we have GraphX being about 3 times slower than GraphLab. Now the LiveJournal dataset's 69 million edges. It's not a small graph, but for a big distributed system, it's not all that big. And as it turns out, GraphX actually scales a little bit better than GraphLab to larger graphs. So this is a similar benchmark. We're running PageRank again, but this time on the Twitter graph, which is 1.5 billion edges. That's a little bit beefier. And here we see that GraphX is only about a factor of 2 slower. So the lazy Java programmer might attribute that factor of 2 to Scala overhead, garbage collection, what have you. But I mean, we're all here for a Spark meetup. We all trust the JVM. And it's pretty fast. So as it turns out, we believe that a lot of this performance gap is due to the fact that GraphLab is able to exploit shared memory parallelism for all the threads that are operating on a graph on the same machine. Whereas Spark and GraphX, therefore, has to go through the full network stack even when it's communicating between partitions on the same machine. And that's sort of pretty core to Spark's architecture and really does have a lot of benefits, but hurts us in terms of communication costs in this particular example. And if you look at that, it actually ends up being about a factor of 2 increase in communication in this benchmark. And we think that's responsible for most of this performance gap. Okay, but these performance numbers are for this, this PageRank example. And I said that that's not really the full picture. So let's look at the full pipeline. So here we're going to take an example pipeline, this Wikipedia example. The Wikipedia example is really nice because Wikipedia has these nice XML dumps and puts it all on the internet and anyone can use it. It's a really nice data set. It's a pretty rich data set. So what we're going to do is we're going to extract the hyperlink graph from the articles using Spark, using our flexible data parallel system, doing this extract, transform, load job that Shivaram mentioned that Spark is really good at. We're going to do PageRank using whatever graph system I'm benchmarking. And then we're going to extract the top 20 pages, once again using Spark for post-processing. So when we do this, we see that Spark by itself is not so fast. But when we implement the GraphX optimizations, taking these lessons from these graph parallel specialized systems and put that in Spark, we now achieve performance parity with GraphLab. So what this means is that you have the ability to do your entire pipeline in one system. You can write all your code in Scala. You don't have to switch between systems. You don't have to write these complex interfaces. And you don't have to sacrifice any performance. That's a pretty big win. So GraphX is about 3,500 lines of code. It's basically a library on top of Spark. And we've implemented all these operators and all these optimizations. We have these Pragle and GraphLab APIs that I mentioned that provide a little bit richer programming interface than the raw GraphX operators. And on top of these APIs, and also directly on top of the GraphX operators, we have a small and growing library of graph algorithms already implemented. And most of these are just a few lines of code. So we have traditional graph algorithms like PageRank and connected components. We have social network analysis algorithms, community detection algorithms like triangle count. We have machine learning algorithms like LDA. So I have all of those different categories that I mentioned represented. GraphX was part of the latest Spark release. It's an alpha right now. We're still doing some debugging and some performance tuning, things like that. But we want people to start using it. We want collaborators, we want feedback. We want to know if you're using it, what's working, what's not, any questions you have, any feature requests. And if you want to start playing with it, you can do that right away. We were part of the latest AMP camp at Strata a month or two ago. And the tutorials and the programming guide from that is all online. You can either Google AMP Camp 4 or go to ampcamp.berkeley.edu. So I'm from Berkeley. I'm from the AMP lab. We're a research lab. So we didn't just stop here. GraphX and these graph analytic systems are still under active development and active research. My collaborators Ankur and Joey are looking at how to extend this GraphX programming model, which pretty fundamentally deals with static graphs, as most of these systems do, and seeing how can we extend that to streaming graphs. What if we want to model time-revolving relationships, things like that. I'm a databases student, so I'm looking at what happens if we want to combine serving graph structured data and graph analytics, maybe even in the same system. What are the implications for a database system? What can stay the same? What do we have to change? So in conclusion, it was these composable domain-specific views and their specialized operators and these specialized efficient operators that enabled us to write a system that can efficiently span the entire pipeline of the entire graph analytics pipeline. From your raw data to your ETL stages, your graph analytics, refinement of your graph, post-processing. The whole thing can all be done in Spark. And we were able to implement this system efficiently by looking at graphs through the lens of database research. And by recognizing that this graph parallel pattern is actually really just some relational algebra operators. And drawing on the rich history and rich literature of distributed join optimization, efficient query evaluation, and such from the databases community. Thank you very much.
So we're pretty over schedule. If we have one question, take it, and the rest can be offline.
Okay, so the join optimizations that you use to make this all much more efficient.
Yes.
It sounds like they were done sort of in the guts, of accessing sort of properties of, in the guts of Spark. Is that right?
No, we didn't have to modify core Spark at all.
I see. Even when you use this routing table.
Yeah, so that's, GraphX is a separate package in Spark. It probably, so it uses some of the maybe less commonly used parts of the Spark API. We do a lot of map partitions work. But no, we didn't have to implement them, we had to understand a lot of the guts of Spark internals, but we didn't have to modify them.
I see. Anyway, are there any thoughts about maybe making these kinds of joint optimizations more accessible in Spark more generally beyond just in the internals of GraphX? It seems like, right, joint optimization would be useful.
Agreed. So as a databases student, I think query optimization is great, and Spark needs more of it. And actually, so Shivaram mentioned Catalyst. So this is really one of the big steps forward in terms of getting query optimization into Spark. So I have to confess I'm not the biggest expert on core Spark, but it's pretty much a physical data flow engine. So query optimization would be something that's implemented on top of Spark. And Catalyst is a way to take a query and sort of extract the abstract, my understanding of it at least, and extract the abstract syntax tree. Say that 5 times fast. And then once you have that, then you can start to play the games with query optimization, things like that. And once you have your query plan, then that's what will be actually executed in Spark. So I think the lessons we learned from the joint optimizations could be applied, but it's not really something that would be put into Spark directly, if that makes sense.
Sure, and then also your manipulation of the cache to do these incremental updates, that's in the guts of Spark.
So cache is not a real cache. Well, it is a real cache. It's a user level cache. It's just what we store. It's how we store the RDD.
Yeah, so you're not talking in that case about the Spark cache itself.
No, not the Spark cache management. No.
All right, let's thank Dan one more time. All right, before you go, I just have a few announcements since it's every meetup or period is full of new things in our community. Spark 0.9.1, which is a maintenance release, is being voted on right now. Spark 1.0 is on the horizon, which is a huge milestone for the code base. There were 2 months of development that will end on April 1st. Then that's when we'll have a code freeze for 2 weeks. We'll be performance testing and fixing bugs until April 15th, when the first release candidate will be cut, and then voting will begin for Spark 1.0. So that's pretty exciting. It will contain a bunch of new features that some of which have already started to get merged in. The next meetup will actually be all about one of the most exciting ones to hit with 1.0, which is Spark SQL. So it was merged into the code base already. And it essentially is multiple components. If you take a look at the Jira and the pull request. And the next meetup will be April 8th in downtown San Francisco at TAG. And will be presented by Michael Ambrose, who gave a talk at the summit in December, the first summit on Catalyst. So check out that meetup and go check out what Spark SQL has to offer, which essentially in one line is interoperability between SQL queries and Scala or Spark Core, essentially. And then maybe less technical, but still very exciting as far as our community goes. Spark, since the last meetup, Spark has become a top-level project. So congratulations to all of us. That means that essentially it means that we had to go through the pain of renaming our URL and mailing lists, as you all know, to get rid of that incubator word. The Spark Summit is coming up quickly. Most significant is that the submission deadline for talks is April 11th. So again, still a little over 2 weeks out, but get your talk submitted so that the program committee, which is going to be already kind of assembled from a lot of the core contributors in the community, can vote on your abstracts, and you can stand in front of the hundreds of Spark enthusiasts. And the summit itself is going to happen June 30th to July 2nd. So we've got a few months before that. Another cool thing that happened outside of the Berkeley Amp Lab but still within the core community is Uyala released their job server, and it's it's like one of the flagship early projects that were kind of like built. It's been talked about by Uwe Yala at the summit, for instance, that builds on top of OpenRealm Spark. And then finally, I wanted to thank Databricks for providing the live stream and the YouTube video that goes up after every meetup, and so that 30 plus people could tune in virtually tonight and to every meetup. Yeah.
Do you know when Shark 090 is finally released?
Shark 090? I don't know. Dave?
It's soon. I think it's maybe 2 weeks, I'd say, something like
Yeah.
that. Yeah.
So Matei says 2 weeks. Let's say within the next couple months.
That's what people told me.
I was hedged. Okay, that's it. Thanks for coming tonight, and we'll see you at Tagged to learn about Catalyst on April 8th.